Hello everyone, my name is Dr. Ambu Misra, and in this video we will be discussing about excitation of cardiomyocyte, its contraction and the action potential of cardiomyocyte. There are various applications of this and we will further dive into it when we proceed into the video. So let's first discuss about the action potential. We all know that there are four phases in cardiac action potential. Unlike skeletal muscle where the information propagates through a nerve and the release of neurotransmitter, that is acetylcholine, which further released from the terminal ends of a nerve and released at a neuromuscular junction, then in turn acetylcholine binds to its receptor and which further causes opening of voltage with sodium channels and influx of sodium occurs from extracellular fluid into the cytoplasm of the cell. But here in case of cardiomyocyte, the action potential is generated by SA node, which further propagates via AV node, and then from the bundles it goes to all the throughout the ventricles and all the other structures of heart. So whenever the action potential arises, let's just say at this place, there is opening of sodium channels. So there occurs influx of sodium from extracellular fluid into the sarcoplasm. Now we are also already familiar that the resting membrane potential or the transmembrane potential of a cardiomyocyte when it is in resting stage or in diastole is minus 96 millivolts. So why is it only 96 millivolts? Why not less or more? It is because this is the equilibrium potential of potassium ions. As we all know that in resting stage there is more potassium inside of cardiomyocyte and there is more sodium and calcium outside the cardiomyocyte, that is in extracellular fluid. So in resting stage the predominant cation is your potassium ion. So that's why the resting membrane potential of a cardiomyocyte is minus 96 millivolts. So this action potential causes depolarization of cardiomyocyte, and further this potential reaches to plus 53 millivolts. So why only 53 millivolts? It is because it is the equilibrium potential of sodium ions. Because sodium ions are the ions that are responsible for depolarization of cardiomyocyte. So sodium influx occurs until this potential reaches the equilibrium potential of sodium ions. At this very stage where there is end of phase 0 and starting of phase 1, the closure of sodium channel occurs and there is opening of potassium channels. These potassium channels that are opened in phase 1, these are transient and they close immediately after phase 1, and immediately after phase 1 there is opening of called slow and delayed rectifier potassium channels. So here there is efflux of potassium ions, that is we say rapid and transient, and here this potassium channel is slow and delayed. Further in phase 2, which is called plateau phase, there is also influx of calcium ions from extracellular space into the sarcoplasm, that is through calcium channel. Now this calcium is going to play a huge role in contraction of cardiomyocyte. Further there is a efflux of sodium, efflux of potassium ion continues in phase 3, and yet again in phase 4 There are some leaky potassium channels that are still open, which are responsible for restoring the resting membrane potential to again to minus 96 millivolts. So now let's put an emphasis on these calcium ions. Okay, so we have seen throughout these axial potential phases that there are movement of ions throughout to and through from extracellular compartment into the intracellular compartment and vice versa. But ultimately this gradient of ions needs to be restored so that whenever the next axial potential arrives, the cardiomyocyte is in the same stage as it was earlier. So there are two channels which are responsible for restoring this gradient. The first one is your sodium potassium pump, which causes 3 sodium to move out and 2 potassium to move in. The another one is your sodium calcium exchanger. Here there is movement of 3 sodium ions towards inside and 1 calcium ion to outside. So these 2 channels are responsible for restoring the ionic gradient that was reversed, or you can say due to the depolarization and further throughout the axial potential. So these 2 channels help in restoring those ionic gradient. Now there is a term called cardiac excitation and contraction coupling. What is cardiac excitation and contraction coupling? Cardiac excitation, contraction, coupling. What happens here? So wherever there is electrical stimulation of cardiomyocyte, which in turn causes actin myosin cross bridge formation, and further it causes contraction of cardiomyocyte. So this is basically how the axial potential causes your contraction of cardiomyocyte, is your cardiac excitation and contraction coupling. But the main mechanism that is responsible for cardiac excitation and contraction coupling is your calcium induced calcium release. We will see here, these ions are either in extracellular compartment or in intracellular compartment. This calcium in phase 2, which moves inside from extracellular to intracellular compartment, that is in the sarcoplasm of cardiomyocyte, this calcium is responsible for further causing contraction, but this calcium is insufficient to initiate the contraction, to cause actual contraction of cardiomyocyte. So what happens now? This calcium goes and it in turn binds to ryanodine receptors, which are primarily present on your sarcoplasmic reticulum, which is the main source of calcium ions during the contraction of cardiomyocyte. So let's draw a rough diagram of a cardiomyocyte. So this So this is your sarcolemma. This is your extracellular fluid or extracellular compartment. This is intracellular fluid or intracellular compartment. Here is your sarcoplasm. This is your sarcoplasmic reticulum. This thing is called T-tubules. This is T-tubule. Here we have our L-type calcium channels. This this here is your ryanodine receptor. Okay, so this is the store of lots of calcium ions. So this calcium, which is present in extracellular compartment, this is this calcium. So this calcium, when it moves inside into the cardiomyocyte through these L-type calcium channels, this is insufficient to cause muscle contraction. So what it will do now, it will go and it will stimulate these ryanodine receptors. These are ryanodine receptors type 2. Wherever this calcium goes and stimulates this ryanodine receptor, there is a release of this stored calcium into the sarcoplasm. Now this calcium in turn goes and binds to troponin C, one of the subunit of troponin complex. We have troponin C, troponin I and troponin D. So it goes and binds to troponin C. What it does to troponin C, that it causes unmasking of attachment site for the myosin head, which is present on actin filament. So let's just say this is your actin, and here is your troponin C. It goes and it binds. So this is your attachment site for myosin head. This will slide it further. So now it's unmasked. The position where the myosin head is going to attach is now unmasked, so that the myosin head can bind to actin. So calcium goes to troponin C. There is unmasking of myosin head attachment site, which in turn causes cross bridge formation. Now there is a formation of cross bridge, but this needs ATP to cause movement of these filaments and further contraction. So the myosin head, it contains ATPase enzyme, which causes dephosphorylation of ATP, then energy is released and further causes the sliding, and sliding in turn results into your contraction of cardiomyocyte. So this is called calcium induced calcium release, where the calcium that is present in extracellular compartment, which comes inside the intracellular compartment during the extrapotential, which further stimulates the ryanodine receptors. There is a release of stored calcium from the sarcoplasmic reticulum, and this in turn goes and binds to your troponin C, which causes unmasking of attachment of myosin head site, and further there is formation of cross bridge, and through the help of ATPase, ATP is broken down, energy is released, and there is sliding of filament suckers, which in turn causes the contraction. Now the thing is, from everywhere the calcium is coming into the sarcoplasm. So this calcium needs to go back to its original plane, like it was earlier when action potential was not arrived, when the cell was in resting stage. So for this calcium that is present in sarcoplasm, this again needs to go back into the sarcoplasmic reticulum. For this we have this channel. This is called SERCA pump. Now let's discuss about this SERCA pump. SERCA stands for sarco endoplasmic reticulum calcium ATPase. So how this calcium goes through this SERCA pump, back into sarcoplasmic reticulum. This happens by a binding of calcium to a protein called sequestration. When the calcium binds to sequestration, then it goes back via SERCA pump back into SR. That's how the calcium that was pulled inside the sarcoplasm goes back into your sarcoplasmic reticulum. And the other ions which came inside or went outside from the cardiomyocyte that goes into extracellular compartment, and the ions that comes inside, they are restored via these two pumps, sodium potassium pump and sodium calcium exchanger. So so we can conclude that the movement of ions that has occurred after arriving of action potential, now all these ions are back into their places when the action potential was not arrived, like it was in resting stage. Now further, let's discuss about refractory period. Refractory period. What actually is a refractory period? So whenever the action potential arrives at the cardiomyocyte, there is a change of ionic gradient. Ion moves from inside to outside and outside to inside. So can the cardiomyocyte be stimulated again during this phase? So there are two types of refractory period. First, let's understand that. One is called absolute and the other is called relative. So what is absolute refractory period? During absolute refractory period, how much action potential you give, how much stimulus you give to the cardiomyocyte, they are not going to get stimulated. But in relative refractory period, if you give sufficient stimulus, the cardiomyocyte can be activated. So how long does this refractory period last? It lasts at the beginning of phase 0 till somewhere in between in phase 3, like somewhere in between phase 3, from the beginning of phase 0 and somewhere in between phase 3, this absolute refractory period lasts, and there is no stimulus that can be given which can stimulate cardiomyocyte in this period. And what about relative refractory period? The rest of the stage, rest of the phase 3 that has left out after absolute refractory period is your relative refractory period. So from there until end of phase 3 is your relative refractory period. So in relative refractory period, if a stimulus given that is strong enough, it can stimulate the cardiomyocyte. So what is the significance and what is the mechanism why we cannot, any stimulus that is given in absolute refractory period cannot stimulate cardiomyocyte, and why if a strong enough stimulus is given in relative refractory period, it can actually stimulate your cardiomyocyte. So we know whenever the action potential arrives, there is opening of voltage graded sodium channels. So now this sodium channel is open and it is not going to stop, or you cannot alter its functioning until it reaches its equilibrium potential. That is, whenever we see from here until here, in this period your sodium channel is open and there is continuous influx of sodium ions, and any stimulus cannot alter its functioning during this period. It will be closed only when it reaches its equilibrium potential, that is plus 53 millivolts. So there is no way that this sodium channel can be opened again, even because it's already open. You cannot open something which is already open. So this is absolute refractory period. But still it continues till here, like somewhere here. in phase 3. Why? It closes at this stage, but it is still not recovered. So the sodium channels are going to recover fully somewhere here. So when they are fully recovered, now at this stage, during this phase, the sodium channels are recovered, and if you give an stimulus that is strong enough, it can open these sodium channels again even before action potential is reaching its resting stage. So that is your relative refractory period. So now, as we know, like in skeletal muscles, the stimulus travels via the membrane of your skeletal muscle. But in case of cardiomyocyte, the cardiomyocytes are arranged in such a way that every single cardiomyocyte is attached to one another, and there are gap junctions. These gap junctions are made of a protein known as conaxin proteins. So there are gap junctions which are further made up of conaxin proteins. These conaxin proteins allows movement of ions from one cardiomyocyte to the adjacent cardiomyocyte, and it allows movement of your sodium ions, calcium ions, and your potassium ions. So this allows, let's just say this is your one cardiomyocyte, this is your adjacent cardiomyocyte, and here we have your conaxin proteins, which are actually responsible for movement of those ions in between two adjacent cardiomyocytes. So as you know, in resting stage, the predominant cation inside the cell, inside the cardiomyocyte, is your potassium ions. So these potassium ions, they move through this channel and goes to adjacent cardiomyocyte, which in turn stimulates the sodium channels that are present in adjacent cardiomyocyte, and this ion stimulates those sodium channels, which in turn causes opening of sodium ions, this sodium ion channel. So this way it depolarizes the adjacent cardiomyocyte. But these sodium channels, the sodium ion can also pass through this. So the way of adjacent cardiomyocyte getting activated is mainly through your sodium ions. The main ion that is responsible for activation of adjacent cardiomyocyte is your sodium ions. So whenever sodium ions moves from one cardiomyocyte to the other one, it goes and it raises the membrane potential to a less negative value. Let's just say from minus 96 millivolts, it raises it until like minus 80 or minus 75. So whenever this sodium ion raises the membrane potential of the cardiomyocyte, this in turn causes opening of voltage gated sodium channel in the adjacent cardiomyocyte. This way, the adjacent cardiomyocyte keeps on activating the further cardiomyocyte, and the whole ventricle and whole of the heart is activated. Now, this is like how the action potential propagates throughout the ventricles. Now we will see different types of ryanodine receptors. So this is your ryanodine receptor. How many types of ryanodine receptors do you know? There are actually 3 types. Type 1, type 2, and type 3. So what are locations where these different types of ryanodine receptors are present? So the type 1, it is present in your skeletal muscle. The ryanodine receptor type 2 is present in your cardiac muscles. the third one is present in brain and other tissues. So why is it important to know about these receptors? Okay, so whenever the ryanodine receptor is defective or mutated, we see certain pathologies. So what are these pathologies? So starting from type 1, you have heard of a thing called malignant hypothermia. So whenever your type 1 ryanodine receptors are defective or mutated or not functioning properly, what you get is malignant hypothermia. Malignant hypothermia. What is malignant hypothermia? Whenever you give a patient some volatile and inhalating anesthetic agent, such as your halothane or isoflurane, and also some muscle relaxants like succinylcholine. So whenever you give this, and if your ryanodine receptor type 1 is defective, this will cause malignant hypothermia. So what are the agents that cause this? So the agents are volatile, inhalating, anesthetic agents, such as your halothane and your isoflurane and your muscle relaxant like succinylcholine. So if there is a patient whose ryanodine receptor type 1 is defective or mutated, and you give these agents, the patient will end up in malignant hypothermia. So what are the symptoms of a patient who has been ended up into malignant hypothermia? So the patient will have increased body temperature, as we know from the term hypothermia. There will also be rhabdomyolysis, breakdown of your muscle protein, and you will have arrhythmia. You will have increased body temperature, rhabdomyolysis, and arrhythmia in patients of defective ryanodine receptor type 1 who has malignant hypothermia when getting injected with these agents. Okay, moving on to your ryanodine receptor type 2. So what happens if your type 2 ryanodine receptors are defective, which is present in your cardiomyocytes? You will get ARVD type 2. What is this? This is arrhythmogenic right ventricular dysplasia type 2. You will have arrhythmogenic right ventricular dysplasia type 2 if your ryanodine receptor type 2 is defective, which is primarily present inside your cardiomyocytes. So what happens in this case? So as you know, the ryanodine receptor type 2, the ryanodine receptors as a whole is responsible for release of calcium ions. So in this case, if they are less functioning, there will be increased calcium inside the sarcoplasm. So there will be calcium overload. So calcium overload, what it will cause further? It will damage your cardiomyocytes, and in turn your cardiomyocytes are actually replaced by fibrofatty tissues, and it is replaced by fibrofatty tissues. So if a normal cardiomyocyte is replaced by fibrofatty tissues, there will be it is going to affect the contractility of your ventricles, of your right ventricles. So now the right ventricle will not be able to contract properly. Further, it will also cause arrhythmias. What kind of arrhythmia? You also get arrhythmias when there is ischemia. But this kind of arrhythmia, it is non-ischemic ventricular arrhythmia. So you will get non-ischemic ventricular arrhythmia. Non-ischemic ventricular arrhythmia, which is primarily originated from your right ventricles. So we just saw defect in right receptor type 1, which causes malignant hyperthermia. What are all the agents that are causing it, and the symptoms, and the right receptor 2 mutation or defect, which causes ARVD type 2, which causes calcium overload, and which in turn damages your right ventricular cardiomyocyte, and the right ventricular cardiomyocytes are replaced by fibrofatty tissues, and it also causes arrhythmia, that is non-ischemic ventricular arrhythmia, that are primarily originated from your right ventricles. Okay, there is no proper pathology associated with type 3, and we don't need to discuss about it here. Let's discuss the another pump that we just discussed, that is your SERCA pump. So how many types of SERCA pump do you remember? Actually there are 3 types of SERCA pumps, as we know. So, and there are further subtypes of those types, so we will see all of them. So type 1 is actually, it is mainly present in your fast twitching muscles. SERCA pump type 1 is present in your fast twitching muscles. There are further 2 subtypes, subtype A and subtype B. Type 1A is present in adults, and type B is present in neonates. Further, type 2. So type 2 also has 2 subtypes, type A and type B. Type 2A is present in your cardiomyocytes or cardiac muscle, and also in slow twitching muscles. Type 2A is present in cardiomyocytes or cardiac muscles, and also in slow twitching muscles. And type 2B is present in almost all types of cells. And what about type 3? Type 3 is present in non-muscle tissues. Non-muscle tissues such as your epithelium and your neuronal tissues. So SERCA pump is also of 3 types, and there are further categorizations. So type 1 is present in fast twitching muscles, type 1A is present in adults, type 1B is present in neonates. Type 2 also has 2 subtypes, that is type 2A and type 2B. Type 2 is present in cardiac muscle and also in slow twitching muscles, and type 2B is present in almost all types of cells. And type 3, it is present in non-muscle tissues, that is your epithelium and your neuronal tissues. Now let's quickly see what are the pathologies associated with these pumps. So first one, if you have defective SERCA 1A, if you have defective SERCA 1A, the patient is going to have known as Brody's myopathy. Brody's myopathy. So what is Brody's myopathy? Whenever there is defect in SERCA 1A, you will get Brody's myopathy, and in this condition, there is inability or deficiency for muscle to relax. Like muscle is unable to relax, or deficient to relax, or unable to relax. So there is inability in muscle relaxation, or you can say deficiency. There is deficiency in muscle relaxation. Further, if we have defect in SERCA 2B, when there is defective SERCA 2B or mutated SERCA 2B, the patient is going to have Darier's disease. Darier's disease. This is Darier's disease. What happens in Darier's disease when there is defective SERCA 2B? The patient will have wart-like lesion on skin. So where is SERCA 2B present? It is present in almost all types of cells. That also includes epithelium. So wherever SERCA type 2B is defective, you will have wart-like lesion on skin. Now, what if your SERCA 2A is defective? Where is SERCA 2 is present? It is present in cardiac muscle and also in slow twitching muscles. So focusing on SERCA 2A that is present in cardiomyocytes, you will have cardiomyopathy, that is due to defect in calcium movement. So what will happen if SERCA 2A is defective? You will get cardiomyopathy, and what feature you will see in this kind of cardiomyopathy? You will see that there is a reduced contractility of cardiac muscle and also heart failure. So SERCA pump is of three types. We have seen the subcategorization and the defects. SERCA 1A, defect in SERCA 1A causes Brody's myopathy. Defect in SERCA 2B, SERCA 1A causes Brody's myopathy. SERCA 2B causes Darier's disease, and SERCA 2A causes cardiomyopathy, where you will see reduced contractility of cardiac muscle and also heart failure. Now we have seen the calcium ions play a really important role in contraction of cardiomyocyte. So can we say that calcium ion, it actually determines the inotropic state of heart? So can we write that calcium ions, they determine inotropic state of heart? Yes. So calcium ions, mainly those which are present inside the sarcoplasmic reticulum, they actually determine the inotropic state of heart. Well, what is inotropic state? Inotropic means the extent of contraction of your cardiomyocytes. So we are familiar with some inotropic agents. See, inotropic agents can be of two types. It could be like positive inotropic agent or negative. So positive inotropic agents, they increase heart contractility and heart rate. So inotropic agents, these are agents which increases or agents that stimulates myocardial contractility. They increases myocardial contractility. So what are inotropic agents we are familiar with? We all know of beta adrenergic agonist. Beta adrenergic agonist. These are positive inotropic agents, and in physiological state, which is present inside the body, the agent that is present inside the body, what are those agents which are positive inotropic agents? So we all know whenever the sympathetic system is activated, there is surge of adrenaline and noradrenaline. So these are also positive inotropic agents, right? So first we can see epinephrine and norepinephrine. Epinephrine primarily binds to beta receptor. Beta receptors are beta 1, 2 type beta 1 and beta 2. So epinephrine stimulates both beta 1 and beta 2. And norepinephrine primarily stimulates beta 2 receptors. Okay, so the other agent which is a drug is your dobutamine. Dobutamine is a drug that is positive inotrope and it primarily binds to beta 1 receptors. So can we say that these two are non-selective beta adrenergic agonists, and this is your selective beta adrenergic agonist. Why non-selective? Because it binds to both beta 1 and beta 2, but dobutamine will only going to bind to beta 1. Beta 1 is primarily responsible for contractility of heart. Beta 2 is also responsible, but not in that extent as beta 1. So how in turn it increases the contraction and contractility in turn. So these agents, they causes increasing intracytoplasmic calcium. These agents, whenever they bind to their corresponding receptors, they increase intracytoplasmic calcium, which in turn increases contractility and also heart rate. So what all conditions can you think of where you need to increase contractility and heart rate of your heart? Can we say in acute decompensated heart failure and also in cardiogenic shock? In these two conditions, we really need to increase the contractility and heart rate of your heart, of the affected heart. So what is the mechanism that is going to imply in order to increase this intracytoplasmic calcium by these beta adrenergic agonists? We will see this. So whenever these agents bind to the beta receptor, primarily the beta 1, so whenever this beta 1 receptor is stimulated by these agents, this signal is going to get carried out through G protein coupled receptors. This G protein coupled receptor in turn activates your adenylyl cyclase. Okay, so now your adenylyl cyclase is activated. Now what? Now this in turn is going to convert ATP into cyclic AMP. Now this cyclic AMP is going to activate protein kinase A. This cyclic AMP is going to in turn activate your protein kinase A. So what is the function of protein kinase A? It has two functions. What are the two functions? The first, it stimulates L-type calcium channels, which in turn increased calcium influx in from sarcolemma. This protein kinase A stimulates L-type calcium channels, which in turn causes increased influx of calcium ions. It also stimulates MLC kinase. What is MLC? MLC is myosin light chain. It also stimulates MLC kinase. And what is the function of MLC kinase? It is going to phosphorylate your MLC. Myosin light chain kinase is an enzyme which in turn phosphorylates myosin light chain. So what happens when myosin light chain is phosphorylated? So myosin light chain it in turn increases actin and myosin interaction. So there are two ways by which beta adrenergic agonists are going to increase the cardiomyocyte contraction and heart rate. That is, one, by stimulating L-type calcium channels and by increasing actin myosin cross bridge formation. So we just saw like how the beta adrenergic agonists like epinephrine, norepinephrine and certain drugs like dobutamine works to increase cardiomyocyte contraction and heart rate in case of acute decompensated heart failure. This is your acute decompensated heart failure and in cardiogenic shock. Perfect. Now, what if there are certain conditions where we need to decrease the contractility and heart rate? So if we have to decrease the contractility of heart and also the heart rate, we need certain drugs or agents that are called calcium channel blockers. These are calcium channel blockers. So what all examples can you remember of calcium channel blockers? We will see. We have heard of verapamil, your diltiazem, and your nifedipine. So what is verapamil and diltiazem? These are categorized into non-dihydropyridines, and your nifedipine is your dihydropyridine. Okay, so this is dihydropyridine. pyridine, and this is your non-dihydropyridine. So how they are actually going to work in order to reduce the heart contractility and heart rate? These agents are going to target those calcium channels. These are going to target calcium channels. They are going to block them, and which in turn blocks calcium channel, which in turn causes decrease in intracytoplasmic calcium ion, which in turn decreases contractility and heart rate. So what are the conditions that you can think of where you need to decrease the contractility of heart and also the heart rate? That is your angina and arrhythmia. So in these conditions like angina and arrhythmia, we are going to use calcium channel blockers, which primarily functions by blocking the calcium channels, which in turn causes decrease in number of calcium ions inside the sarcoplasm or cytoplasm, which in turn causes decrease in contractility and your heart rate. So why in angina we need to block your calcium channels? Because in angina there is blockage. This is in case of coronary artery diseases, there is blockage in one or some of your coronary arteries. So there is decreased oxygen supply to the particular part of that heart which is supplied by that particular coronary artery. So if there is less oxygen, the heart will need more oxygen in order to function properly. So if the heart needs to function like it usually does when it's normal, it will need more ATP, more energy and more oxygen, and that we don't have because the coronary arteries blocked. So what we will do, we will block calcium channels, which in turn will reduce the contractility. If the contractility is reduced, there is less need of oxygen. Now this will suffice the extra work that is needed by the part of your heart that is getting less oxygen. So it is to decrease the overload in cardiomyocyte, which are already getting less oxygen. And in arrhythmia, just to decrease heart rate, for example, in case of SVT or supraventricular tachycardia. In supraventricular tachycardia, we need to reduce the heart rate. So we will give calcium channel blockers, which will in turn causes blocking of calcium channels, and which in turn reduces your contractility and also the heart rate. So this is it for today's class, or we will say video. In next class we will be discussing about the concept of prelude and afterload, and all the mechanism and the basic concepts and the basic principle, and further the pathologies that are underlying those mechanisms. So this is it for today. Thank you. Have a great day.